Welcome. In this video we will look on several problems, how to find a local minima and maxima and along with that set of points using the method I explained in the first video for section 15.1. So let us look on the examples. In the first example, find the local minima, maxima and saddle points. These problems are always formulated this way because once we look for local minima and maxima, the method gives us the saddle points also. For a function fxy is 2x squared plus y to the power of 4 minus 4xy plus 1. So first step, we need to find critical points. Those are points where the gradient of f is equal to 0. Our function is defined nicely, the derivatives are defined, we will see that. So the critical points which where the gradient is not defined don't exist. And when we split this equation into components, that spells out fx equal to 0 and fy equal to 0. So in other words, to find critical points, we need to solve where fx equals to 0 and fy equals to 0. We compute those derivatives. Fx is 4x minus 4y. Fy is 4y cubed minus 4x. We set them equal to 0. And typically this will be a system of equations which is not linear. So the basic method we will be using is substitution. So for substitution we look for the, in some sense, simple equation. That's the first one in our case. When we simplify, we get that y is equal to x, and we substitute that to the second equation. When we substitute, we get 4. We substitute for y, so x cubed minus 4x equal to 0. So 4x, so we get 4x, x squared minus 1 equal to 0. And we see there are three solutions, 0 and plus or minus 1. That's not the answer. The critical points are points, pairs of xy. So for every x, we need to compute the corresponding y based on the substitution. So if x is equal to 0, y is equal to 0. X is 1, y is 1, and x is minus 1, y is minus 1. So that tells us we have 3 critical points. So that's the end of the first part. We have 3 critical points. Alright, so let us look on the second part, which is the second derivative test. Alright, the second derivative test starts with computing the discriminant. The discriminant is defined as the determinant of 2 by 2 array made out of the second order partial derivatives arranged the way I'm just writing, fxx, fxy, fyx and fyy. We compute the partial derivatives. There are 4 fxx, fxy is minus 4, fyx is minus 4, and fyy is 12 y squared. That's done based on the first order partial derivatives. In particular, we see that what we discussed in section 14.7, these two second order mixed partial order derivatives are the same. And we evaluate this discriminant, so we get 4 times 12 y squared, that's 48 y squared on the main diagonal, minus 4 times minus 4, that's 16 on the secondary diagonal. We don't need to simplify much. We will be evaluating, we just need a nice formula so that we can easily evaluate. So now we will go step by step over all the critical points and decide using the test. So the discriminant at our first critical point 0, 0 is when we plug in x equal to 0, y equal to 0, we get minus 16, that's negative, we have a saddle point. For that you need to remember how the test goes. For the next critical point 1, 1, the discriminant at 1, 1 is 48 minus 16, that's positive. I don't need the actual value, just to decide it's positive. So we will have a local minima or maxima. We still need to look at fxx as the test says at 1, 1. That's the value here, 4, doesn't depend in this case on x and y, so that's 4, that's positive, so we have a local minima. And finally the third critical point, minus 1, minus 1, the discriminant is 48 minus 16, that's positive, fxx at minus 1 equals 4, that's positive, so we have again a local minima. So then we are done, no more critical points, so we can formulate the answer. We have one saddle point at 0, 0, two local minima at 1, 1 and minus 1, minus 1. We didn't find any local maxima, so we add that there are no local maxima. And we are done with the answer for the problem. Alright, so let us look on our next problem, example 2. Same formulation, find local minima, maxima, saddle points. That's quite typical for these problems of fxy, which is x plus y times xy plus 1. Alright, we know the procedure, so the first step is to find the critical points. That means looking into where the gradient is 0, which, as I explained in the first example, is equivalent to solving the system where the two first order partial derivatives are 0. We can take the first order partial derivatives from the function as it is, but it's a product, we would need to use a product rule. If I distribute the formula for the function x plus y times xy plus 1, I get x squared y plus xy squared plus x plus y, and I can take the derivative in a much simpler way. So then the fx derivative comes to 2xy plus y squared plus 1. The fy derivative comes to 2x squared plus 2xy plus 1. We set them equal to 0. And we start thinking about how to solve this system. Again, it's a nonlinear system, but now both of the equations are about of the same level of difficulty. On the other hand, we notice that there are many terms in both of the equations which are the same, 2xy and 1 and 1. So in that case, it's worth trying to subtract the two equations. So this is our second method for solving this system, subtract. The two equations, that means subtract the left hand and right hand sides from each other. Doing that, we get y squared minus x squared. That's the simplified version of the difference of the left hand side, equal to 0. In other words, y squared equal x squared. So not completely ready for substitution, but definitely a big step forward, because if x squared is y squared, there are only two cases, two possibilities to consider: x equal to y as a substitution, or x equal to minus y. So let us look on the two cases. If x is equal to y, we substitute, for example, in the first equation, and we get 2x squared plus x squared plus 1 is 0, which is 3x squared plus 1 is 0, and there is no solution, because the left hand side cannot be ever 0. If x is equal to minus 1, again we can substitute to the first equation for fx and get that minus 2x squared plus x squared plus 1 is 0, which simplifies to x squared is 1, and we get two solutions: x is equal to plus or minus 1, and that gives us two critical points. If x is 1, going back to the substitution we used, which is x equal to minus y. So y is minus 1. If x is minus 1, y is the opposite. So we have two critical points, 1 minus 1 and minus 1 1. And that finishes the first step. The second step, again, is the test. So we start with our discriminant. It's a determinant of the following 2 by 2 matrix or 2 by 2 array. We need to compute the partial derivatives. Using the first order partial derivatives on the previous slide, we can compute the second order partial derivatives, and they are 2y, 2x plus 2y, 2x plus 2y, and 2x. Compute the discriminant, we get 4xy minus 2x plus 2y squared. And again, that's a nice algebraic formula. We don't need to simplify anymore because we will be plugging in anyhow. So at the first critical point, 1 minus 1, what do we get? When we plug in x equal to 1 and y equal to minus 1, we get value minus 4, negative, so that's a saddle point. And when we plug in x equal to 1 and y equal to x equal to minus 1, y equal to 1, that's our second critical point. As it happens, we get again the value of the discriminant minus 4, that's negative, so we have another saddle point. We are done because we tested all the critical points. So the answer is that this function has two saddle points, one at 1 minus 1, one at minus 1 1, and no other, so no local minima or maxima. Alright, so again you see the two-step procedure for finding first the critical points and then testing them one by one. So let me close this video with one additional problem so that you have a variety of problems to study from, how to compute and how to find the local minima, maxima. So let us take a problem which has a little bit geometric flavor. It comes from our book. So example 3, and it says find the shortest distance. The shortest is stressed such that we see that we are looking for minima distance from the point 2 1 minus 1 to the plane x plus y minus z is 1. Alright, so we have a plane, we have a point, and we want to find the shortest distance here. If we write down the formula for a distance, that requires in the formula second roots. So if I set up a function fxy being equal what the problem is asking, namely the distance, I will have a complicated function to take a derivative of because of the roots. So instead of that, just because of the derivatives I'm going to take, I will work with square of the distance. And the idea behind this step is that if I find the shortest distance, the square of it will be also the shortest. I just need to keep in mind what I find. So we will set up a function for the square of the distance. So it's if I have a point x, y, z on the plane, the distance to my point 2 1 minus 1 and square of it is given by x minus 2 squared plus y minus 1 squared plus z plus 1 squared. That's not satisfactory because this formula depends on 3 variables and I want a function of 2 variables, but we know that the point xyz is on the plane, so not all 3 xyz are independent. For example, I can write z in terms of x and y. From the equation of the plane, we can write that z is x plus y minus 1 and plug it into our formula. So we get x minus 2 squared plus y minus 1 squared plus z x plus y minus 1 plus 1, so that's x plus y squared. So now we have a nice function depending on x and y, and we want to find a minima of fxy. And by the problem, there is only one minima, so actually we are looking for a local minima. So first we will find critical points. So let's do that on the next slide. So critical points, they are given by fx, which when I compute the fx derivative, it's 2x minus 2 plus 2x plus y, set it equal to 0, and fy, which comes to as 2y minus 1 plus 2x plus y, set it equal to 0. Alright, so we need to solve a system of 2 equations. They happen to be actually both linear equations, so let's simplify them. The first equation, when we simplify, spells out I can cancel the 2's as a factor, so x minus 2 plus x plus y gives me 2x minus 2 plus y equal to 0. After simplification, the second equation comes out as x minus 1 plus 2y equal to 0. And for example, we can eliminate x by taking the second equation, multiplying by minus 2 and adding to the first one. So when I keep the first equation, I have 2x minus 2 plus y equal to 0. Multiply the second equation by minus 2 gives me minus 2x plus 2 minus 4y equal to 0. Add these two equations together, I get minus 3y equal to 0, so y must be equal to 0. And then going to any equation above which has x in it, I can compute that x is equal to 1, and that's the only solution. Alright, so we have one critical point, and that's 1, 0. 1, 0. By the geometry of the problem, this has to be local, this has to be minima, but we should check. Okay, so we will work through our test. We need our discriminant, fxx, fxy, fyx, fyy, which when we compute the derivatives, there are 4, 2, 2, 4. The discriminant is 16 minus 4, that's 12, and that's positive. So even d evaluated at 1, 0 will be 12, and that's positive. To decide, we need the fxx derivative, which is equal to 4. That's this derivative. That's positive. So the test tells us that we really have a local minima. So let us formulate the answer. The shortest distance is. So now remember that the function was set up as square of the distance. So the shortest distance is the root of f at the local minima 1, 0 which is, we just plugging into the formula for f, we got minus 1 squared plus minus 1 squared plus 1 squared, second root of that, so we get second root of 3. And this distance is realized, or is a distance to the point xyz on the plane, which is 1, 0, and when we compute z from the plane equation, we get 0. So the shortest distance is root of 3 to the point 1, 0, 0 on the plane. And that's our full answer here. And I showed you this problem such that you see that sometimes thinking one step ahead, which function you really want to use to interpret your problem can save you some algebraic work. So in this particular case, instead of the formula for distance, we use the square of a distance such that we don't need to work with so many second roots. All right, so those are the practice problems for this section, and this was the end of the video for this section. Thank you. Bye now.